Now we are going to start with the double angle section. So we'll solve our next problem. So problem is a double angle discontinuous strut. Double angle discontinuous strut is to carry a factor axial compression, of 178 kilonewton. The length of the strut between the centers of intersection of intersection is 3.08 meter. Design the member of following two cases. Design the member of following two cases. So the first case is angles placed back to back on opposite sides of gusset. So what does that mean? So you have this gusset plate and you have this angle sections which are connected back to back on opposite sides of the gusset plate. Then the second case, angles placed on same side of gusset. So what does that mean? This is your gusset plate and so that's an angle. So they are on the same side. So these are the IS Indian standard angle section. This is Indian standard angle section. So these are the two cases. This is the case number 1 and this is your case number 2. So we need to calculate first of all the different angle we need to try. Then we need to just consider the class of the section. Then we can go ahead with the design capacity, and for both the cases we will calculate the design capacity. So that's our solution would be. The problem, it is given that there are the double angle discontinuous strut is given, and that is to carry a factored axial compression of 178 kN, while the length of the strut between the center of the intersection is 3.08 meter, and we need to design it for the two cases. So we'll go ahead with the solution. So when you talk about solution, we'll have the step number 1. Consideration of angle section. Consideration of an angle section. So for that we need to go ahead with the page number 48, and there is a clause 7.5.2.1. Okay, to calculate the effective length, so we'll go ahead with that clause. This is the clause 7.5.2.1. the clause. This is for the double angle strut, and it is given that the effective length KL in the plane of end gusset shall be taken as in between 0.7 and 0.85 times the distance between intersection. So we need to just consider this part 0.7 to 0.85 times the distance between intersection. So that is according to the clause 7.5.2.1. This is page number 48. So let us calculate the effective length. So we can say, assuming effective length which is equal to 0.8 times L. So this is 0.8 times 3080 if we consider it in mm. So you will get here L effective, that is the effective length, which is equals to 2464 mm. So this is from the clause number 7.5.2.1, page number 48. Now we need to calculate the required area, how much area is to be needed for this load. So we can just consider design stress from the table number 9. Page number 42. So from page number 42, we can assume a design stress. So this is the page number 42 where we have the table design compressive stress for the column buckling class. So this is KL by according to KL by R ratio, we can assume the design stress. So from this, if we just consider Fy yield stress, that is of 250. So let us assume a 90 MPa stress. So we are just going to assume here. So assuming again design stress and that is equals to 90 MPa. So this is again from the table number 9, page number 42. So we got the stress. Now we know the formula, stress equals to force divided by area. So from there we will get the required area. So therefore we can write down required area will be equals to load divided by stress, and load is already given in the problem, that is 178 kilonewton. So this is equals to 178 into 10 raised to the power 3 divided by 90 MPa. So here you will get it around 2000 mm square. So this is the total required area for the both double angle. So if you just consider area of each angle, so you will get therefore area of each angle would be equals to half of that. So that is 1000 mm square. So just we need to consider around 1000 mm square, whoever is having the area. So from the steel table, you have to just check the whichever angle is having around 1000 mm square. So I'll just try this angle, try two angles 80 by 50 by 8 mm, and for that you will get the properties in that table itself, steel table itself. That is area is 978 mm square, nearly 1000. Ixx is also given here, 61.90 into 10 raised to the power 4 mm raised to the power 4. Then Iyy will be equals to 18.5 into 10 raised to the power 4. Then you got Rxs is equal to 25.2 mm, and Ryy it is 13.7 mm. So that is all about the step number 1. Now we'll go for the step number 2, where we will just check what kind of section we are having, or the class of the section. So we'll go ahead with the step number 2. That is class of the section. So we have provided area, that is say area provided, that is equals to 2 into 978. 978, that is 978. So that is around 2000 mm square. Approximately, you can say. Now we need to go to the table number 2, page number 18. Now here we just need to check what is the d by t. So we just need to calculate d by t. So here are the ratio is given for the different cases. If it is internal element of compression plane, so you have this b by tf. This is wave. In that case, this is d by tw, wave of channel. Angle is given. Then we have single angle or double angle. Then here it is angle is given, compression due to bending, and then there are the different circular hollow. So there are different web of channel, stream of T section, likewise there are different ones. So we just need to calculate what is the d by t ratio, and we just need to check this is the angle or compression due to bending. It has to be in terms of 9.4 or 10.5 or 15.7. So accordingly we can just cover it. If it is less than 9.4, so we can say that that is the plastic. If it is 9.4 to 10.5, then we need to consider it as the compact class 2. If 10.5 to 15.7, that it would be semi-compact. So therefore d by t so we are considering here this 80 mm one divided by thickness is again 8 mm, so this is going to be 10 mm, not mm, actually it is 10, so this is less than 10.5. So therefore we can say the section is compact. So from clause, this is actually table 2, page 18.